My experience in senior design can be described in one word: stressful. This is the course that separates the men from the boys. We actually get to see if we can apply the book knowledge and theory that we were taught and make it into something real. So it was really hard for me in the beginning to see if I'd be able to cut it. It turned out that our project was a success, but we put in a lot of time. I mean, spending nights here, days here, a lot of time. I had to come up on a lot of learning curves. I actually got to use a technology that was in one of my internships with some isolator software doing printed circuit boards. And this actually helped me in the design and the etching of our printed circuit boards.
What we're doing now is MPEG-2 compression. The top one is real time and the bottom one is after the MPEG-2 codec. It's an ATM device. What it does is send 3 to 5 megabit per second MPEG-2 video over ATM networks. Our project was to make it work over T1 lines, which most corporations already own. ATM isn't too prevalent at this point. So we just kind of decided what the minimum or maximum number of T1 lines was and used IBM equipment in order to make it work. And that's the general gist. We found that iframe and IP frame MPEG-2 video works fine over T1 lines. The video quality varies greatly between 3 and 5 megabits. So at 3 megabits, what we have right here, you can see macro blocks, the pixels, 16 by 16 pixels. When it moves quickly, you can see the video kind of break up. There's a 180 millisecond delay. The only additional delay to this would be the speed of light between ATM switches. So it's a pretty fast, good for video conferencing, video on demand, teleeducation, things like that.
My name is Jeremiah Cohn. I'm a senior in computer engineering. What we've been doing here is developing a arcade game system, which will hopefully have some innovations to the arcade system. Today, it allows you to retain your progress in a game, which is something that is not currently available in arcade games. For instance, Mortal Kombat or something like that, you play for $5, a couple hours or whatever, and that money is completely used up, and you start at the same place. Your skills may be better, but you haven't actually gained anything in the game. In our system, you have cards, which would allow you to maintain your player data and retain things that you do in the game. For instance, collecting treasure, improving your character's strength and abilities, which would allow for continued play in the arcade setting, which is something that is not there yet. I think it'd be really neat. And so we've been trying to show that it's possible. And you can select any card you like, a knight, a wizard, or a thief. And swipe your card. Here's a wizard. You can fight and eventually be able to improve in this game. This is just a simple demonstration. Improve in the game world, gain access to new areas you could not get to before. It may take hours and hours of play that you could not normally do in a regular arcade game. Yeah, you can fight, for instance. You want to go ahead, give it a try. That's attack and that's move. You can't attack, I'll fight for you. Ben over there is battling you, and he does more damage because he has a big sword and you're a little wizard. And you were killed. But anyway, ideally you'd have magical attacks that would fireballs and whatnot, which are in the works as well.
Okay, what we've got here is a model train controller that uses a personal computer to interface with a model train. We used a Windows NT based machine to create a Windows 95 application, graphical user interface. It's meant for a young physically impaired child who likes to use trains but has difficulty using the traditional model train controllers. So what we've done is created a window here that will interface via serial port and our hardware to access the train and control the train's speed, horn, and lights. And this particular train doesn't have the horn and lights capability, but that option is available. So I'll do a quick demonstration. You can, there we go. You can get the control the train with pulse wave modulation signals that we can vary the duration to get a different varying speeds. So if we can go from the low speed to the max speed, which is full throttle. So that'll be that's the full throttle that this train allows. Essentially, we use the basic stamp module, which allows us to send out PWM signals and amplify that PWM signal via the H-bridge, which allows us to send the train up to 17 volts. We decided anything above that would probably derail the train, so we set a max at 17 volts. I think that's about it.
What we did, our project was with the microelectronics lab here at NC State University, and pretty much what we did was we used a different type of photo mask to process some wafers. And these masks are a lot cheaper than typical chrome masks, and it gives about the same resolution. And our results were good. We got great alignment, great measurements. So, and the advantage of this is a low turnaround time. We can make these masks in-house in about a day, as opposed to about 20 days for masks for productions. And they cost about $300 a piece, as opposed to about $6,000 a piece for the regular production mask. So it's going to save a lot of time and a lot of money for the department. And like I said, the results are good, so it looks like it's going to work out pretty good.
Hi, I'm with the Senior Design Group. What we did was use FPGAs to make 5 different projects. The idea of our projects was to integrate Altera chips into the Digital Logic Lab. This project, again, uses an FPGA. The FPGA is right here, and this project is a helicopter project that we started in another class, but we just added on to it using an FPGA. Using a key press, the whole thing shuts down. But then when you start it up, it'll come exactly to horizontal. So I just press start and wait a few seconds, and it's going to build up RPM. You can see on the meters right there how fast the motor is spinning and how much current that the motor is drawing. And this is a level control. As you can see, it's exactly horizontal right now. Now when you perturb the system, it undershoots, overshoots, and they'll come down to exactly level. Here is a home security system on the floor. We actually built this thing in Digital Logic class, but our senior design kind of builds upon the Altera chip, and we did use an Altera chip when we had that class. So what it does is I'm gonna put it in reset state. It asks me to set the system password. I flick the switch up. I enter a password code. I entered 123. Take the password set switch down, and the system is disarmed, and the LED light comes on when the system is disarmed. So now it's waiting. You can exit. When you exit a door, a red light comes on, or if you open the window, a red LED comes on right there, and there's another door and a window on the side. Now, say you want to leave the house and you want to go shopping. Well, you want to arm the system. So you enter the passcode 123, and it waits 8 seconds while people leave, and then the system will arm. And you'll see the light come on when the system is armed. There it is, system is armed. And you may not be able to hear it, but there is a voice that goes along with this. So now, say an intruder enters the house. You open the door, and it says system alert, and it wants you to enter the password. If you don't enter the password, then the system alarms. And you may, I don't know if you can hear it, but the system is alarming. Now to disarm it, you enter the passcode, 123. System is disarmed. And that's the whole idea of the project. It also has a remote panic. And there it is, it's alarming again. Enter the passcode, and the system is disarmed. Again, this just proves the flexibility of Altera chips, and our projects worked very well. Thank you.
Well, basically what we have here is our project which was sponsored by Autotronics, Darrell Fulton here. And basically what he was looking for was to design an anti-collision detector interface module for dynamic vehicle control. Now, in this design, the approach that we wanted to take was, through a feasibility study, we found that there are 3 emerging markets for products of this type, and they are highlighted down here. We have a Type 1, which is a warning, which gives like warning alarms of some type. Then we have a Type 2, which also gives warning alarms, but also takes control of the vehicle in some form, such as braking or steering. And then Type 3, which is where everything is going, is total autonomous vehicle control. That is basically you get in your vehicle and tell it where you want to go, and you get there safely. But right now we're not there. So basically what we did with this project is we designed an interface with an open system interface module approach, whereas it would simply form an interface between a Doppler radar unit, our system, and any automobiles, any auto manufacturer's automobile. And basically what goes on here is that the Doppler radar unit emits a frequency, a Doppler frequency shift that represents the closing speed of 2 vehicles. That frequency, that difference frequency, is fed to our frequency to voltage converter here. It is converted to a 0 to 5 volt voltage, which now represents that same speed. After it's converted to an analog voltage, it's then digitized through this 8-bit analog to digital converter, and then fed to an internal PIC microcontroller. Now that microcontroller, once it's in there, can go through further processing to make sure that the data is reliable, and it could also interface into the automobile's onboard computer. Now, through a feasibility study, we found that 100% of the cars manufactured today have an onboard computer, which does a lot of the processing in the car, and all the data is actually there. So actual integration into a vehicle today would not be too difficult, and this system is actually geared toward that functionality. And well, that's basically it. Once it goes into the car's computer, it could go to control braking or steering, or simply give some type of warning indicator, thereby satisfying the condition of all 3 possible markets for this particular device.
What we have here is Jenner. He's a distributed robot. He's a biped walking robot. It's basically a proof of concept model for distributed field bus technology. What we do is we're basically controlling a rotating master, and along with that master moves 3 slave motors, and then also the 2 feet, which are controlled by themselves. You can see it's leaning to one side right now. When it reaches that state, it'll pick up a foot and rotate. Right now we've got him walking in a circle because we don't have a lot of area to deal with. The idea behind this is, for the most part, walking robots are controlled by a central computer. With this model, it's controlled by a network of 9 microprocessors, each of which is very low power and doesn't consume a lot of real estate.
Okay, this is a device designed for the blind to keep them in the center of a crosswalk when they're crossing an intersection. And I'll demonstrate what it does. If they go too far to the right, it'll make this sound. If they go far to the left, it'll make this tone. If they stay in the center, it should be a continuous tone.
We can have groups that include people at all levels, sophomores, even freshmen, sophomores, juniors, and seniors, because freshmen will say, well, what can I do? I'm just barely starting college and I haven't had any engineering courses. All of these people come in, they're bright, if they're motivated, there's something they can contribute. And so they give something and they also receive something from the experience. And I think that's a real exciting part of it. The companies likewise appreciate the opportunity to be able to work with the students. Sometimes the companies gain surprisingly from the efforts of the students. We've had situations where companies admitted having things developed that were going to save them a lot of money We're going to provide opportunities to them that they did not have previously. And these are typically things that they thought were pretty important and useful, but because they have so many things to do, they just did not have the staff to be able to handle everything. And therefore, they turned this project over to the students, and the students did an excellent job.
Pretty much what we have is an electric racetrack, but we have a Mitsubishi microprocessor hooked up to it so that you can race against the computer or let the computer race against itself. And we have, the way we do this is we have sensors located underneath the track at various turns, and the computer can then tell where the car is and make speed adjustments. And when you're racing against the computer, you can choose an easy or a hard mode depending on how much of a challenge you want to have. Mitsubishi is hoping to test the versatility of one of their microprocessors, the M16C, and they're just, it's used for a wide variety of applications, and here it's on the, like the toys and the racetracks, just showing the wide variety of uses for the microprocessor. All right, so here we're going to let the computer race itself. It just went into demo mode right now. We can put in how many laps, just let's say 4, and we hit start, and it counts down, 3, 2, 1, and then off they go.
The goal of this project was to design an autonomous robot capable of competing on a predefined track. The competition was for IEEE, the Institute of Electrical and Electronics Engineer, and it was spearheaded by the local student branch. 2 seniors worked on it, and we also had a group of underclassmen to help with us as a learning experience for the underclassmen. The robot needed to follow a white line throughout the track, had a couple of different objectives. One was to push a button on the side of a wall. Another one's to go up a hill, which is usually kind of difficult in robotics because the motors are not powerful enough generally. And we were able to do that. And we also were able to detect turns and things like that. There were other things that we needed to do that we didn't show today in our demonstration, but at one point we actually had to pick up a ball bearing and drop it off at another location. And we had to navigate through a mine type area without any type of sensing. Some of the things that made this project interesting is, one, the ability to work with the underclassmen and actually show them what they're going to be doing in senior design was very rewarding, because kind of a way of giving back what you've learned and wishing that when you were in their position you had that opportunity, so that now when you're doing this project you're not completely lost. And not only that, it was just the type of project we were working on, just very rewarding in the sense that a lot of different technologies using microprocessors, analog circuits for sensing, sound detection, using light, so a lot of different elements that come into play that usually you don't get in your core classes.
Okay, our project was to implement a way for the race team to measure how far up and down the car was traveling while it was on a racetrack during a practice session. Last spring, they had developed a way for them to measure the tire temperatures, engine speed, and wheel speed. This will give them real data while they're running on the track so they can better set up their car when they come in for the races. Okay, to measure the wheel travel, we're using a voltage divider circuit and a variable resistor. When we change the resistance by going up and down, what happens is it changes the voltage. This voltage is sent into an analog to digital converter, converted to binary data, and transmitted over a modem to the laptop computer, which then translates it back into inches so that they can visually see on the laptop how far up and down the car is moving.
Yeah. It'll kill it.
experience, like I said, was very stressful, but I feel very pleased with the work that I've done. I actually feel like I have a right to walk out of this university as an electrical engineer. My advice is keep the program. I don't know how anybody could have gotten through without it.